All right. I'm Siavash Rezazadeh, a research scientist at the University of Texas at Dallas. And today I want to talk about different parameterization that we can use for control of powered multi-joint prosthesis to improve the gait of above-knee amputees. To give you a little background, we have sought for a parameter named the phase variable that can parameterize human gait. And we have used this setup to, for some reason it didn't play. We have used this setup to characterize and investigate and compare different parameters that can do this role for us in a study that was done by a student in our lab. So one of the parameters that we came up with was this parameter, the angle of the orbit in the face portrait of thigh angle. It works pretty well in a steady state walking when you are walking on a treadmill with constant speed. But as you see, it has immediate problem when you change conditions, when you don't have this orbit anymore. When you change speed or stop walking, the orbit would shrink and then control would collapse. So to solve this problem, we came up with another idea, another phase variable, which was based on a holonomic parameterization. A holonomic parameterization is good because it doesn't depend on the speed and can work from stop to maximum speed, any condition that you want. But the problem is that it cannot be continuous. So we made up a finite state machine with two different phase variables, both of them holonomic. Different colors shows different phase variables. So that it can work in all the orbits and different conditions. Also, we added another state that can detect backward walking just for another condition that can be covered. We tested this controller with an amputee subject for forward walking over ground with different speed from stop to start, for backward walking, and crossing obstacle, walking on treadmill with very slow speed and very fast speed, all with the same controller. So we did a mocap analysis of this controller with powered leg with the baseline passive leg of the amputee. And it showed that significant improvement in all these kinematic parameters that determine the quality and symmetry of the gait. The holonomic phase variable is good because it can work in different conditions, but it has a problem. And the problem is that it cannot follow exactly human gait during push-off and touchdown. I don't get into math now, but it becomes mathematically singular around that point. So we used a combination of holonomic and non-holonomic parameterization in order to get a specifically better push-off and get to better speed and better quality of the gait. So this is preliminary test of this controller on a human subject on a very high speed and maximum incline of the treadmill. We'll be doing amputee tests with this controller hopefully soon. And let me conclude this talk with our new prosthetic leg, which is very low impedance and at the same time very high torque. It can have almost knee-free swing, which is very beneficial for efficiency of the gait and also natural looking of the gait. And it's And its low impedance, low joint impedance makes the actuator sort of transparent to the controller and makes it enable for a wide range of controllers to be applied on this leg. Thank you very much.
So you didn't want to get into the mathematics of why the holonomic controller becomes singular near push-off and touchdown, but that generally represents either a loss of information or a loss of actuator freedom or some other loss of control capability. So what structurally is involved without the math?
Well, the thing is that when you have a holonomic constraint,
What's a holonomic controller?
It's not a holonomic controller per se, it's a holonomic parameterization, meaning that you parameterize the knee and ankle trajectories based on a constraint to the thigh, which is holonomic. Okay? So when you do that, to answer your question, when you do that, it requires that the joint velocities become zero at the same moment. Whereas in human gait, it doesn't happen. So when the thigh angle becomes zero during push-off, when it reverses its direction, or during touchdown, it requires ankle and knee velocities also become zero, which is not possible unless you have a singular system, which is sensitive, and as you said, is not easy to control. So that's why I moved to a non-holonomic constraint to get around that problem.
So your motivation is to find a phase variable which can be used also for transient gaits, right? Because at the beginning of your talk, you said the phase variable, original phase variable, cannot be used, can only be used for steady state gaits. And
no, that was the phase variable that was the sort of the background section, the phase variable that we originally worked with. And it was good only for a steady state. When we changed the speed and or we walked over ground from stop to start and back to stop, it would not behave very well.
Can be used in those cases as well?
Yes, as you saw, it could go. Yeah.
when you restrict motion to sagittal plane, would it generalize to 3D walking gaits like turning around the circle and things like that?
For lateral motion, you mean?
Yeah.
Well, we don't have actuator for lateral motion. If you have actuator for lateral motion, then sure, why not?
Only one single phase variable would be sufficient to
well, we haven't done a study on that, but I can't see why not. Just a speculation, it should be possible.
Just a clarifying question. So in the three-dimensional space of hip angle, knee angle, and ankle angle, you're restricting the motions to be some closed curve, and that's what you mean by holonomic control?
Yes.
And except for that you have a double-valued function, that's the same as hybrid, as zero dynamics?
Double value function. What?
And then for a given hip angle, there might be two knee, because you have some closed curve in the three-dimensional space instead of a single
Exactly.
single
That's
arc.
why it shouldn't be continuous. It should be a finite state machine. In hybrid zero dynamics, they reset the phase variable from one leg to another, right? So it's not continuous. The same thing here. That's why we designed a finite state machine.
So it's not a closed curve. It's an arc that you're going up and back and you're resetting.
Well, it is.
Do you have two variables that are slaved to one, or do you have a closed path in the three-dimensional space?
Yes.
The second, yeah.
Second, yeah. We have a closed curve, but in the top side of the curve and bottom side of the curve, we have different phase variables. If I go back to.
So the state machine is so you can use the hip angle as a slave.
Yes.
Okay. It's a master, I mean.
Yes.
Sorry.
Yes, that's master.
Okay, maybe in the interest of having a little bit more time for lunch, we'll stop here and thank the speaker one more time. authors of the